we move on to the proof of fact 2, which we repeat here for ease of reference. Fact 2 involves the definition of the term delta 2 of s times x and the bounding of its norm by 2 times c times delta times the square root of n times epsilon. This bound holds for any vector x that has unit norm. In the definition of delta 2 of s, we have, as we had in the definition of delta 1 of s, three sums. 1 over index r representing powers of s, 1 over index k representing filter coefficients hk, and another one over index I representing graph Fourier transform entries. We begin the proof of fact 2 with a focus on the innermost two sums. We write the eigenvector decomposition of S as V times lambda times V Hermitian and bring the eigenvector matrix V to the front of the sum. This allows us to write the expression in 45. Notice how inside of the sum, powers of S in the left-hand side are replaced by powers of lambda in the right-hand side. The term within brackets, the one that is nested between V and V Hermitian, is a diagonal matrix. This is true because it is the sum of the diagonal matrices lambda to the power of r and lambda to the power of r plus 1 multiplied by scalars. We define a matrix to represent this term. Since the matrix depends on the eigenvalue lambda I, we will denote it as G sub I. We state this definition in equation 46. Using the definition of Gi in the equality in 45, we can rewrite it as we show in 47. This is just using the definition. The result looks misleadingly simple. The matrix Gi has a complicated expression. The key step in the proof of fact 2 is to manipulate the entries of G sub I to show that, complicated though they look, the entries of Gi actually do have simple expressions, and that, more importantly, we can bound the entries with the integral Lipschitz condition. To work on these manipulations, we write the diagonal entries of G sub I explicitly in equation 48. Recall that since Gi is a diagonal matrix, these are the only non-zero entries that this matrix has. To obtain 48 from 46, we replace the eigenvalue matrix lambda with the eigenvalue lambda j, whenever that lambda appears in 46. We do this because we are looking at the jth diagonal entry of Gi, and lambda j is the jth diagonal entry of the eigenvalue matrix. To continue with the processing of the entries of Gi, we differentiate the cases in which j equals I and in which j is different from I. For the case in which j equals I, the expression for the entry Gi sub jj in 48, we are actually looking at the entry Gi sub ii. In this particular case, the terms inside the sum in equation 48 are such that I and j are the same. Thus, the product lambda I to the k minus r times lambda j to the r is just lambda I to the power of k. Likewise, the product lambda I to the k minus r plus 1 times lambda j to the r plus 1 reduces to lambda I to the power of k, because indexes I and j are the same here. Both of these facts hold true for all r. Thus, as was the case of the proof of fact 1, compare the derivation we are doing here with equation number 40, the derivative of the frequency response makes an appearance. We have that the ith entry of the matrix G sub I is given by 2 times lambda I times h prime of lambda I, as we show in 49. For the case in which j and I are different, the innermost sums in 48, the ones that are over index R, are geometric sums. This allows for their computation in closed form. We show the resulting value of the sum in 50. You can compute these geometric sums on your own to verify that 50 is correct, or not even. It's not very relevant to understand the proof. What is relevant is to use the explicit form in 50 back in 48. When we do that, we end up with sums that make the frequency response of the filter appear. They are the terms h of lambda I, which comes from the summation of hk times lambda I to the power of k, and h of lambda j, which comes from the sums involving the sum of hk times lambda j to the power of k. Therefore, we can reduce the jth diagonal entry of the matrix Gi to the expression we show in 51. It is time for us to make the crucial observation in the proof of fact 2. That observation is that the integral Lipschitz hypothesis applies to both the term that appears in 49 and the term that appears in 51. The bound in equation 6 applies to 49, and the bound in equation 5 applies to 51. Therefore, the norm of the matrix Gi, which, being diagonal, is the absolute value of its largest entry, is bounded by 2 times C, as we show in 52. This completes the core of the proof of fact 2. The rest is some simple algebra of matrix norms. However, we do need to verify that this is true, so let us do that. We begin by taking norms in 47 and leveraging the sub-multiplicative property of the operator norm. The norm of the product of matrices in 47 is thus rewritten as the product of the individual norms of each factor. This gives us the expression in 53. In 53, the norm of the matrix V and the norm of the vector Vi are units, because the matrix V is unitary and the eigenvector Vi is normalized. The norm of the matrix Gi is bounded by 2C. This is the bound we have endeavored to establish. It is stated in 52. This is one of the critical observations to make in 53. The other critical observation to make in 53 is that the norm of EI is bounded by the eigenvector perturbation lemma. That's the reason why we derive this lemma. The specific claim is that the norm of EI is, at most, epsilon times delta. The bound is stated in equation 9. We can therefore bound 53 as in 54. At this point, we must recall that we have been concentrating in the two innermost sums that appear in the definition of delta 2 of S in equation 44. We need to add back the sum over GFT indexes. Making it so, our manipulations lead us to the bound we show in 55. We now use the triangle inequality to bound the norm of the sum in 55 as the sum of norms of each summand. We end up with terms that have the form that appears in 54. Using the bound we show in this equation allows us to write the bound in 56. We now need to observe that the sum of the absolute values of the GFT components that appear in 56 is the one norm of the graph Fourier transform x tilde. The one norm of any vector of a given dimension is bounded by the two norm multiplied by the square root of the dimension. We can therefore bound the one norm of the GFT in 56 with its two norm multiplied by the square root of n. This is where the square root of n term appears. We then obtain the bound we show in 57. Recall finally that the graph Fourier transform preserves energy and that the signal x under consideration has unit energy. Therefore, the true norm of the GFT coincides with the true norm of the signal x, which is 1 because we are considering the computation of an operator norm. This concludes the proof of fact 2 and concludes the proof of theorem 1.